Hello friends, in today's video, let us prove that the retarded potential satisfies Lorentz gauge conditions. So this is part of the lengthy derivation concerning retarded potentials. We had stated the equation for both retarded scalar as well as vector potential. So then we have to prove that the equations for the scalar and vector potentials are true, and for that we need to verify whether these potentials satisfy the inhomogeneous wave equation and Lorentz gauge condition. So in the last video we proved that the retarded scalar and vector potential satisfy inhomogeneous wave equation. Now we will try to prove that these potentials, retarded potentials, satisfy Lorentz gauge condition. So overall, if we prove both of these, then in a way we are actually proving that the Maxwell's equations are not affected with this choosing of retarded potentials. So we know that the Lorentz gauge condition is given by del dot A bar is equal to minus mu 0 epsilon 0 dou V by dou T. So we need to prove that this vector potential and the scalar potential satisfies the Lorentz gauge condition. So first of all, what is the equation for vector potential? It is vector A of r bar comma t is equal to mu 0 by 4 pi into integral j bar of r bar dash comma tr divided by curly r into d2 dash. So to prove this, we need to first find the del dot A. So let us take the divergence of vector A. So del dot A bar is equal to mu 0 by 4 pi into integral del dot of vector j by r d2 dash. So here del dot affects only the terms inside the integral, and the constants can be taken outside of this del dot. So now we need to find del dot of j bar by r. So in order to clarify one small thing about this r, here this curly r in the denominator is not vector r. Vector r is r into r cap. So vector r consists of both its magnitude and its direction. R cap is the unit vector, r is its magnitude. So normally we cannot divide a vector by a vector, right? This kinds of practice does not exist. A bar by b bar is not defined. So here j bar by r, here this denominator r is actually the scalar part of vector r or its magnitude. So normally if we write 1 by r, that simply means it's a scalar. So we usually take del dot of 1 by r. Sorry, del of 1 by r, and if it is r cap by r, that's a vector, so we take del dot of r cap by r. So here we have del dot of j bar by r. Here j bar is a vector and 1 by r is a scalar. So check for the rule of taking del dot of fa, del dot of a scalar into a vector. So you can find the product rule for that and apply that product rule into this equation. So opening up this divergence, taking the product rule, we get this is equal to mu 0 by 4 pi into integral del dot of j by r should be expanded like 1 by r into del dot of j plus j bar dot del of 1 by r d2 dash. So now we have this 1 by r here, and this del of 1 by r, we know the curly r, the magnitude of r is modulus of r bar minus r bar dash. We have said that it's a scalar quantity, and it is equal to the magnitude of r bar minus r bar dash. So del of 1 by r will be del of 1 by r bar minus r bar dash, magnitude of. So this can be equal to, considered to be equal to minus del dash of 1 by r bar minus r bar dash. So here del and del dash are different. In del we take dou by dou x, dou by dou y and dou by dou z. In del dash we take dou by dou x dash. So the coordinates are with respect to the positions of the charge in del dash, and for del it is the x, y and z. So we can see that del of 1 by r bar minus r bar dash, it is somewhat like minus 1 by x square. So here r bar dash is inside a negative sign, so we have to add another negative sign here, minus del dash of 1 by r bar minus r bar dash. So substituting for del of 1 by r here in terms of del dash of 1 by r bar minus r bar dash, I can rewrite this equation to be equal to mu 0 by 4 pi into integral. So for convenience, let me first take this del dot of j bar by r alone. So here we have expanded del dot of j by r, del dot of j bar by curly r, that is equal to 1 by r into del dot of j plus j bar dot del of 1 by r, right? So first let us solve for this and find a term for del dot of j by r, and then finally substitute that here in the equation for del dot of a. So we have said that for del of 1 by r, which is del of 1 by r bar minus r bar dash, we can substitute minus del dash of 1 by r bar minus r bar dash. So doing so, I can write this del dot of j by r to be equal to 1 by r into del dot j minus j bar dot del dash of 1 by r bar minus r bar dash. So here instead of del of 1 by r, I have made this substitution here. Now we know if del dot of j by r is equal to this term, we can write what will be del dash dot of j by r. It will be just like the previous expansion, it will be del dash dot j into 1 by r plus j bar dot del dash of 1 by r. So what will be j bar dot del dash of 1 by r? J bar dot del dash of 1 by r will be del dot j by r minus, sorry, here is a dash, del dash dot of j by r minus del dash dot of j into 1 by r. So instead of j bar dot del dash of 1 by r in the last equation, here this term, I will be substituting the new term here. So what will be the equation for del dot of j by r? Del dot of j by r will be equal to 1 by r into del dot j plus 1 by r into del dash dot of j minus del dash of j by r. So here we have three terms. So if you look closer, we have two terms here. In the first term, we have 1 by r into del dot of j, and in the second term, we have 1 by r into del dash dot of j. These two terms are a little different. So let us calculate what is del dot j and what is del dash dot j. So we know del dot j, its expansion is summation over I dou ji by dou xi, right? Dou j by dou x1 plus dou j y by dou x2 and so on. Here we know the current density j is actually a function of xi dash or r bar dash and tr, right? So if we have to differentiate j with respect to xi, where j is a function of xi dash and tr, we do it like this. Maybe you have seen that if f is a function of x and y and you have to take the derivative with respect to time, how do you do that? We write dou f by dou x into dx by dt plus dou f by dou y into dy by dt, right? So in a similar manner, since we have to take the differentiation with respect to xi and ji is a function of xi dash and tr, it can be done like dou ji by dou xi dash into dou xi dash by dou xi plus dou ji by dou tr into dou tr by dou xi. So here we can see that in the first term we have to take dou xi dash by dou xi. Since xi and xi dash are independent of each other, this first term is actually 0. Only the second term carries, and in the second term we can see we have dou ji by dou tr into dou tr by dou xi. We know what is tr? Tr is t minus r by c, and if you take the derivative or the del of this minus r by c, it is simply minus 1 by c into del, so here it is curly r, del r, right? So this is simply minus 1 by c into dou j by dou tr multiplied by del r. Dou tr by dou xi is minus 1 by c into del r, and dou ji by dou tr is taken here. Now let us find what is del dash dot of j, because we have to substitute here what is the value of del dash dot of j. It is actually quite different from del dot of j. So as we will see, del dash dot of j is equal to summation over I dou by dou xi dash of ji. Here ji is a function of xj dash and tr. So this is equal to summation over I dou ji by dou xj dash into dou xj dash by dou xi dash plus dou ji by dou xi dash, so dou tr into dou tr by dou xi dash. So this will be equal to the following term. So if you look at the first term, you can see here dou j by dou xj dash into dou xj dash by dou xi dash. Here these are not independent. This will be approximately 1 if you sum over I. So dou j by dou xj dash, it is actually equal to summation over I. It is actually minus dou rho by dou t. From the continuity equation, you will study that del dot j is equal to minus dou rho by dou t. For our convenience, del dash dot j is minus dou rho by dou t from the continuity equation if you take the differentiation with respect to space alone. So this part involves that del dot with respect to space alone, and from the continuity equation that is equal to minus dou rho by dou t plus the second term So from the earlier experience, we know the second term is simply dou j by dou tr into 1 by c or minus 1 by c into del dash of curly r. This is del dash, right? Del dash of curly r. Now substituting for del dot j and del dash dot j in the previous equation, let us call this equation number 1. 1 will be modified like del dot of j by r is equal to one by r into, instead of del dot j I am writing minus 1 by c dou j by dou tr into del r plus 1 by r into, instead of del dash dot of j I am writing minus dou rho by dou t minus 1 by c into dou j by dou tr into del dash of curly r minus the last term was del dash dot of j by curly r. So equation 1 will be modified like this, and we know del of r is modulus of r bar minus r bar dash. It is actually equal to negative of del dash of r bar minus r bar dash, because as you can see here del of r bar and here we have two negative signs, so del dash of r bar dash, those are actually 1 and same. So here if we look here, in the first term we have minus 1 by r into 1 by c into dou j by dou tr del r. Here we have another term, it is again minus 1 by r into 1 by c into dou j by dou tr into del dash of r. These two terms will cancel each other because of this rule, del of r is equal to minus del dash of r. So the remaining terms are simply del dot of j by r is equal to minus 1 by r into dou rho by dou t minus del dash of j by r. Now let us substitute for del dot of j by r into our first equation where we begin. Here from here we started. Here we had one del dot of j by r. We found the equation for del dot of j by r in our substitutions. So let us write the equation for del dot of a now. So del dot of a is equal to mu 0 by 4 pi into integral del dot of j by r dito dash, and this is it now equal to mu 0 by 4 pi integral minus 1 by r into dou rho by dou t minus del dash dot of j bar by r dito dash. So here we have a second term here. It is actually integral del dash dot of j bar by r, and that volume divergence can be converted into a surface integral. So for the second term we have integral del dot of j bar del dash dot of j bar by r dito dash, that can be converted into a surface integral with j bar dot n cap by r into dA equal dA, and if we assume that j bar is equal to 0 at infinity, this surface integral will vanish. So if current density is 0 at infinity, the surface integral will be 0. So we can assume this second term to be equal to 0. So we are left with the first term alone. So let us modify that. So we have del dot A is equal to mu 0 by minus mu 0 by 4 pi into integral 1 by r into dou rho by dou t into d tau dash. So I am going to multiply an epsilon 0 in the numerator as well as in the denominator. So the new equation is del dot A equal to minus mu 0 epsilon 0. I am going to take this dou by dou t to the outside of the integral. Since it is commutative, I can do like that. Dou by dou t of 1 by 4 pi epsilon 0 integral rho by r d tau dash. So simply the terms inside the square bracket is potential V, right? That is the equation for the retardant scalar potential. So this is simply minus mu 0 epsilon 0 dou V by dou t. So we have proved that the scalar and vector potentials, the retardant potential satisfies the Lorentz gauge condition through this derivation. By substituting for the vector potential A bar from the equation for retardant potential, we have finally obtained the Lorentz gauge condition. So we can say that the vector potentials satisfy Lorentz gauge condition, and in the last video we proved that they satisfy the inhomogeneous wave equation. So overall we can say that the equations for the scalar and vector potentials that we proposed based on our logical arguments actually holds good with all of the basic assumptions of electrodynamics, the basic equations of electrodynamics. And so we have finally concluded that the retardant potentials, the equations are right, and how the potentials varies over time are determined by those equations. I hope this derivation for the retardant potential satisfying Lorentz gauge condition is clear for you. Thank you.